Well, chemistry students, welcome to the concluding chapter of our discussion together of chemistry this year. This will be my last lecture. For some of you, you might want to split this up into a couple of sessions. That's fine. This might be a little bit of a longer one. But we're going to be looking at chapter 20 and discussing nuclear chemistry together, at least giving you a starter, an introduction to the subjects that are involved here if you were to ever look further into the field of nuclear chemistry. Just a reminder before we get started, please do make sure you get all of your previous work into me. Remember, I'm not collecting homework, but just any tests that are due, make sure you get those in as soon as possible so I can get those graded and put into the grade book. That'd be wonderful. This will be our last chapter, as I mentioned, so this will be our last video lecture. In coming weeks, if there'll be review information I'll be giving to you and stuff of that nature. But otherwise, this will be our last video recorded lecture. And if you need any help or have any other questions, please do reach out to me. You can do that, especially through my jess@sojournbaptist.org email account. And I'd be happy to get in touch with you if you need any further help or discussion on any of these matters or ones prior to this. All right, well, let's get into this. So chapter 20A, talk about the nucleus. Nuclear chemistry is concerned with changes in the atom's nucleus that affect the atom's electrons and release radiation. So nuclear chemistry makes sense. We're going to be dealing with the nucleus. And typically what's found in the nucleus is protons and neutrons. So we're going to be talking about protons and neutrons, but there is also an impact with electrons too. And so we'll be kind of seeing this together as we talk about various types of radiation and how to solve problems involving this. So radiation, as defined, is energy transfer without matter between. A good example of this would be the sun warming the earth. So it's a transfer of energy without matter. Energy is produced from a nucleus, and this is another way of describing radiation energy flowing from the nucleus outward. So the discovery of radiation is an interesting one. You can look at this a little bit further, but if you read 20A, the very beginning of this, it introduces us to a man by the name of Henry Becquerel, who was born into a family of scientists. He was the chief engineer of the Department of Bridges and Causeways in Paris and a professor of physics at the Paris Museum. In 1896, he was doing research on certain crystals and how they would phosphoresce, which meant that they would shine forth with light. He was really interested in this. He was curious as to how this glow worked, and he made an unexpected and remarkable discovery. As he was working with some crystals of uranium salts, he noticed that after having been exposed to the light for some time from the sun, he could bring them inside and put them in a dark place where he had some photographic film plates, and they would expose those film plates. And he started to wonder about these rays and how this was working. Combined with him, these mysterious X-rays are a couple by the name of the Curies. Marie Curie and Pierre was her husband, and they started to do work on this further and even received a Nobel Prize in physics in 1903 for the discovery of what they called radioactivity. Pierre would die, and a little bit after that, and Marie would continue a lot of her work, and she would actually receive a second Nobel Prize for her isolation of polonium and radium. Interestingly enough, two of the elements in the periodic table are named after Marie Curie. Polonium, after her home country of Poland, and then curium, also named after her. So types of radioactivity. We have alpha particles, beta particles, and gamma rays. Now this is on purpose not saying particles here on the last one because it is just energy, just rays. But there are alpha particles and beta particles as well. So we're going to look at these three types of radioactivity. So the alpha particle is an energetic helium nucleus with 2 protons and 2 neutrons. So here symbolized by the 2 pluses, we have the 2 protons, and then we have 2 neutrons. This type of radiation is charged with a positive +2, and it's relatively heavy compared to other types of radiation. And as a result, it's relatively easy to stop. Even a thin sheet of paper can stop alpha radiation. And in general, this doesn't cause any significant bodily injury to people except for sunburns. And the alpha is the first letter in the Greek alphabet. Alpha is the symbol that's utilized to describe alpha radiation. You then have beta radiation, which is a high energy electron coming from the nucleus. We'll talk a little bit more about how this happens. But it's formed by the breakup of a neutron into a proton and an electron. If you imagine for a moment a neutron, remember, which has no charge, being thought of as being a proton with an electron inside of it. So beta radiation happens when one of these neutrons breaks apart and the electron shoots out as radiation, as beta radiation, leaving behind a proton. So it looks kind of like that. So a neutron breaks up into a proton and an electron, which is the beta particle of radiation. This is lighter and less charged than an alpha, and as a result, it's harder to stop. It takes inches of wood to stop beta particles or beta radiation. It can enter into skin and do damage. Its symbol is beta. And then thirdly, we have gamma radiation or gamma rays. This is energy just bursting out from the nucleus. It has no matter and it has no charge. And as a result, it's extremely hard to stop. It takes feet of concrete in order to stop gamma radiation. It can cause much damage by penetrating the entire body. And its symbol is the Greek letter gamma. So you notice here from this image, paper will stop alpha. It takes something like glass to stop beta. But notice that gamma goes through all of that, and it takes like feet of concrete in order to stop gamma radiation. Or in this case, we've got pictured here lead. Lead will also do the trick. So question, a beta particle is just a blank that leaves the nucleus. Answer, electron. Remember, this seems like a strange answer. We don't normally think of electrons being in the nucleus, but if you think of a neutron as being the makeup of a proton and an electron, and when a neutron breaks apart, it leaves behind the proton in the nucleus, and the electron quickly exits the nucleus. This is how you can think of beta radiation. There's an electron coming out of the nucleus because of the breakdown of a neutron. The atomic mass of an alpha particle is, remember, you have 2 protons and 2 neutrons, so adding those together, we should get 4. So the atomic mass of an alpha particle is 4. The atomic mass of a gamma ray is, remember, ray, not particle. This should be kind of the tip off here that it's 0, right? It has 0 mass. It's just energy. The book talks a little bit about measuring radiation. There is 3 different ways in which radiation is measured, both by radiation amount, by the amount of absorption of energy that happens, and by the effect that it has on people. So here are the different units that have been utilized to describe how to measure radiation. I'm not going to be doing extensive testing on any of this, but just so at least you've heard them. You have the becquerel, the Curie. These are all based on the amount of radiation. Absorption, the amount of absorption of radiation is measured in Grays and Röntgens, and then also the effect of them in the sievert. So just know that there are some various ways in which radiation is measured. Okay, so now we get to section B, and we'll be talking about nuclear decay. This is a bit of a longer section. All right, so nuclear equations describe the splitting, fusing, or particle emission that happens within the nucleus. This includes a nuclide, a specific isotope of an element. There is alpha particle emission, which whenever that happens, remember I told you that that's 2 protons and then 2, I'll use the equal sign for neutrons, okay? So 2 protons and 2 neutrons. Whenever alpha particle emission happens, the atomic number drops by 2 because you're losing 2 protons from the nucleus. The atomic mass, though, is going to drop by 4, remember, because in order to get to mass, it's 2 protons plus 2 neutrons added together. That's a mass of 4. So the mass will drop by 4, the atomic number will drop by 2. So here's a good example. Here we have uranium 238. Remember, this is the atomic number. Uranium is 92. And the protons plus the neutrons would equal 238 in this particular isotope of uranium. Now, if uranium 238 undergoes alpha particle emission, that means that it's going to lose 2 protons, which is indicated here. We have to subtract 2 protons from this number to get to 90. And then we have to subtract 4 from the atomic mass, which we go from 238 to 234. Now, what we do is we look on the periodic table to see what number is associated with 90, and we find that that is thorium. And so when this undergoes alpha decay, it will go down 2 here, 2 in the atomic number, 4 in the atomic mass. We have a 234 thorium, and we get the addition of, here's the alpha radiation. It's 4,2 helium. Also could be indicated as 4,2 alpha radiation. Okay, so the nucleus before alpha decay looks like this. We have, in this case, we have 9 protons. So this element is fluorine. And if you count up all of the individual neutrons here, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 neutrons. So the atomic mass is the total of those is 19. Now, if we remove the alpha particle, which would be 2 protons and 2 neutrons, we're going to subtract 2 from the protons and 2 from the neutrons. So we should get 7 protons. So now it's no longer fluorine, but now it's nitrogen, and 8 neutrons. Remember, the identity of the element is determined by the number of protons. And you're just going to look on the periodic table to determine what element it has become. But through alpha radiation, you lose 2 protons. So you're going to move 2 steps down on the periodic table, and that will be the new element that it is. And the atomic mass then here after alpha decay is 15, which is 4 less than the 19 that we started with. All right, so write the nuclear equation that describes the alpha decay of uranium-234. So alpha decay implies that an alpha particle is one of the products. So remember, alpha particle is a helium atom with 2 protons, because that's what helium is by definition, and a total mass of 4, which is 2 protons plus 2 neutrons in this number. Uranium-234 is the reactant, so we can put that here. Uranium is U, and remember, uranium by definition has 92 protons, and we're told what its mass is from this number, 234. So it's isotope of uranium is 234. So now we can work backwards to figure out what is the remaining thing. X is the unknown element, A is the mass number, and Z is the atomic number. So how are we going to get this? We're going to ask what number plus 2 equals 92, and what number plus 4 equals 234. The sum of the mass numbers and the atomic numbers must equal the mass and atomic number of the reactant. And so we know A plus 4 has to be 234. So A must be 230. And Z plus 2 must be 92. Therefore, Z must be 90. And then we can look up on the periodic table what element has an atomic number of 90. And as we saw in our previous examples already, thorium is the one that has 90 as its atomic number. Okay, so now let's talk about what happens when you have beta radiation or beta particle emission. The atomic number actually increases by 1. The atomic mass number does not change. So as an example, here we have C14, carbon 14. Note that carbon has 6 protons. Whenever beta radiation is released, what we have is we have a -1, because remember, an electron leaves, it's really pretty much an energized electron leaving the nucleus. And so it has a -1 charge, and it has 0 in the sense of mass. So the way that we show this then is we just, again, can use the same kind of algebra. We can ask the question, what minus 1 equals 6? And so we know that must be 7. And then here, what plus 0 equals 14? Well, It just stays the same, 14. So here's the nucleus before beta decay. Again, we have an example of fluorine. It has 9 protons, and you count the neutrons. Again, we have 10 of them. It's a total atomic mass of 19. But what happens in beta decay, remember, is that one of these neutrons, in this case, we're picturing this one, this neutron is now shown here, splits into a positive, a proton, and an electron. So we lose one neutron, but it becomes now a proton and an electron that then shoots out from the nucleus, forming our beta particle. So after the decay, we have 10 protons now, because remember, we've added a proton that we didn't have before. But we've actually lost one neutron, because remember, a neutron was changed into a proton. So we added one proton, but subtracted one neutron. So the total mass remains the same, because we just added a proton, but subtracted a neutron. And because protons and neutrons are almost the exact same mass, it really doesn't affect the atomic mass of the nucleus very much. So let's do a sample problem of this. Write the nuclear equation for beta decay of aluminum-28. So we know beta decay is, we write beta radiation here, and we put a -1 down below and a 0 up above. And aluminum-28 is the reactant. So we write Al, we write a 28 up here for this isotope, and then we look up aluminum on the periodic table, and we find that it's at number 13. And then we just do the math. X is the unknown element, A is the mass number, and Z is the atomic. So A plus 0 equals 28. A must equal 28. And then for the Z, we say Z minus 1 equals 13. So that must be Z equals 13 plus 1. So Z must be 14. 14 minus 1 equals 13. And there's the problem. Again, remember, then we just look up what is number 14 on the periodic table, and we will find silicon as the element. Okay, well, what about a couple of other interesting cases of radiation? Positron emission. So this is when a proton changes into a neutron and a positron, or a positive electron. That's why it's called a positron, because it's like a positive electron. It looks kind of like this. Again, we use beta as the symbol for this. But what's happened here is we're changing a proton into a neutron. So notice what happens. We lose one proton, but notice that this number stays the same. And that's because, remember, the top number is the addition of protons plus neutrons. So if we lose one proton, but we gain one neutron, so we lose one proton minus a proton, but we gain one neutron, and remember, these are roughly the same mass of 1. We subtract 1, but we add 1. The atomic mass stays the same, 38. The only thing it changes is the atomic number, which goes down 1. So we change from potassium to argon, and plus then this positron, this positive electron. And then you have interesting case of what's called electron capture. This is when the nucleus pulls in an electron, where a proton changes into a neutron. So it's almost like, remember the neutron before, with beta radiation, a neutron would split into a positive, a proton, and an electron that would go out from the nucleus. Well, this is kind of that in reverse. Electron capture, electron comes in, joins with a proton, and becomes a neutron. And here's just an example of what that might look like, where we have silver 106, and it sucks in an electron, and when it does that, it loses one proton, but it gains one neutron. And that's why this number 106 stays the same, because that's, remember, protons plus neutrons. And we, in this case, lost one proton, but we gained a neutron. So -1 plus 1 becomes the same number again, 106. And just the atomic number goes down 1. So instead of having silver, we now have palladium plus an X-ray photons plus energy. Okay, and then you have gamma emission. Now, this is probably the easiest one to show symbolically, because all that happens here is just energy leaving the nucleus. Remember, there are no particles involved in gamma emission. So you just have, what we do is we write something like the word excited, or sometimes they'll write an asterisk like this to say that it's excited. This element is just an excited state. In other words, it has lots of energy. And then on this side, we just show that energy leaving with the Greek symbol gamma, Greek letter gamma, and it's a 0, 0. Remember, it has no charge, it has no mass, it's just 0, 0. And so we have the exact same element on either side of this, the exact same isotope. The only difference is that we have energy that's left, and as a result, this is no longer than in the excited state. All right, so what will happen with a lot of radioactive elements is that they'll go through a decay series because the nucleus becomes unstable. There's either too many or too few neutrons, and so the nucleus will go through a series of radioactive decays trying to come towards a position of stability. It's not always just one decay. Sometimes it can be a series of decays, both alpha and betas, going back and forth, kind of in a stair-step fashion. And this continues until the final nucleus is in a stable place. Here is a picture trying to illustrate this. I know this is really, really small dots on this screen, but just kind of explain what's going on here. On the x-axis here, we have the atomic number. So starting here with 1, we would have hydrogen, and moving upward into the transuranium elements. And then this is the number of neutrons. What you kind of see here towards the beginning, when we're at like atomic number 20, notice that it's about a 1-to-1 ratio. All of the line that's in the very center of this, that's the darkest, notice here on the key on this side of the chart, the more and more red it is, the more and more stable that is. So if it's black, it's pretty much stable. It's not going through any radioactive decay. The more and more blue and even light blue it gets, the less and less stable the thing is. Notice down here, only not even being around for even less, even for a second. Once you get to this dark blue, you're at least staying there for about a second before it radioactively decays into something else. So all of this area that is blue on the outsides of this line are very unstable states, and means that it'll be going through radioactive decay. So early on, you have about 1 proton for every 1 neutron. You see this about 20 and 20. At 40, note here, if we're tracing this out, now notice that we have you have a few more neutrons to the protons. And the further and further along that we go, once you get to 80, note here, if I trace 80 all the way up, it's something like almost like 120. So it's almost 1 to 1.5. So for every proton, there's 1.5 neutrons. So as we go up higher on the periodic table, it requires more and more neutrons in order for the nucleus to be stable. So when we're talking about stability, elements that are not in this band of stability, if they're somewhere in this blue area, that means they're going to undergo radioactive decay until they eventually get to one of these spots on this stair step where it's a stable state. So there are only 2 possible reactions in the radioactive decay series. You can go through an alpha decay, which involves you moving 2 steps lower. Remember, whenever alpha decay happens, you lose 2 protons and 2 neutrons, which means when you lose those 2 protons, you move down the periodic table 2 steps. So in this case, moving from 89 to 87. Whenever something goes through beta decay, remember that's when a neutron splits into a proton and an electron. The electron leaves the nucleus. We actually move up 1 step. So as an example, you might ask the question, how can actinium 89 decay into radium, which is a Z of 88? So in order to do that, in order to move just 1 step down, it would first have to go 2 steps down to francium 87 through alpha decay, and then through beta radiation, or beta decay, it can move up 1 step. Because remember, alpha moves you down 2, beta moves you up 1. So just to give an example of uranium-238, uranium-238 will move down through alpha radiation to thorium-234. Then we'll take 2 beta steps upward back to uranium, but now note it's at uranium-234 instead of 238. And then it goes through alpha again, going down 2 steps to thorium, but now notice we're at 230 versus 234. And then traveling along, it moves to radium-226. Through alpha radiation, goes down to radon-220. Continues moving downward, polonium-218. And then notice what happens here. You have these branches. Now here, we note that we are getting here to lead, but notice that it can go through this in various different ways. It can move down 2 through alpha, then go up 1, and then down again in alpha, then up 1, up 2, and then down through alpha, and then up again through beta. So any of these arrows are paths in which it might take. It could go alpha, beta, beta, alpha, beta, alpha, beta. It could go any combination of these arrows. It could go alpha, beta, alpha, beta, beta, alpha, beta. So you can wherever you see a green arrow, that's beta radiation. Wherever there's a red arrow, it's alpha. And these, this is just kind of showing you the path that it might take trying to find eventually a stable state at lead 206. And this is kind of just the overall look of that chart. So if polonium turns into lead, what kind of decay has occurred? In order to do this, you have to look at the periodic table. So you're just asking the question, how many steps away is polonium from lead? And you find out quickly is that polonium is higher than it, so it has to move down through alpha radiation. What series of decays would be necessary to change plutonium-94 into protactinium? So then here again, you're going to look at the periodic table you have in your book. You're going to find 94 on the periodic table. In this case is plutonium. And then you're trying to get to protactinium, which is at 91. So that's 3 steps lower than where plutonium is. So in order to get there, we're going to have to go down 1 alpha. That would take us 2 steps down. We still need to go 1 more step, but we can't just only go 1 step. So we have to go another 2 steps down, so another alpha down to thorium, and then we can go 1 up through beta, and that will get us to protactinium. You could do this in any order. You could go up first through beta, and then go down to alpha, and then go down 2 more alpha, and still get to protactinium. But no matter what's going on here, it's going to require you to go through 2 alphas and 1 beta. This is because the location of plutonium is, if I could kind of picture this for you, pretty crudely, is 3 steps away. So we're going from here to here. In order to do that, we go alpha, which takes a 2-step decrease, and then alpha again, which comes to this element, which we don't want to be at. So then we have to move up 1, and that's how we get, this is the beta. Beta moves you up 1, alpha moves you back 2. So 2 steps back, 2 steps back, 1 step forward. And that will get us to 3 steps backward. So we needed 2 alphas and 1 beta. So this is just showing you that all natural nuclides beyond bismuth are naturally radioactive. So everything past bismuth is naturally radioactive. All right, now you've heard of half-life, I'm sure, before. You probably had to do some problems in a math class before, like calculating the half-life of something. Half-life is the time that it takes for 1/2 of the nuclei to decay. Shorter half-life means more intense radiation, the quicker that the radioactive decay process is happening. So for just an example here, let's imagine that element X has a half-life of 1 minute. And let's say that we're starting with 20 radioactive particles within the nucleus. Well, after 1 minute, how much will be radioactive and how much will be non-radioactive? Well, after 1 minute, half of it, right? That's what we mean by half. Now, if we spend another minute, how many will be left? That's right, only 5. And if we went another minute, it'd be 2.5, right? And another minute would be 1.25. So every minute we lose half of the remaining that's there. Just to give you an example of some half-lives, oxygen-13 has a half-life of 0.0087 seconds. Bromine-80 has a 17-minute half-life. Magnesium is 21-hour half-life. Also, you get down to uranium-238. It's a 4.51 times 10 to the 9th years, so a much longer half-life. A sample of 192 grams of thorium-234 decays for 96.4 days. At the end of this time, how much thorium-234 is left? Now, remember for that previous slide, you could see that the half-life for this is 24.1 days. So you can figure out from that, if we have 96.4 days that it's happening, we have exactly 4 half-lives. So, because we just take the 96.4 days and we divide by 24.1 days for every half-life, and we determine that we have 4 half-lives. So then we just take the original sample amount. Since there are 4 halvings, 1/2 is multiplied by itself 4 times, or raised to the 4th power. So 1/2 times 1/2 times 1/2 times 1/2. Whenever you're doing this math, remember you just multiply straight across both the top, the numerator, and the denominator. So you have 1 over 2 times 2 times 2 times 2. Right? 2 times 2 is 4, times 2 is 8, times 2 is 16. So 1/16. So the amount of thorium-234 left after this, we take the original, what they told us was 192 grams, we divide it by 16, and we get an answer of 12 grams of thorium that's being left after that amount of days. Okay, so nuclear stability, there is a lot of question as to how is it that the nucleus does stay stable. We've put this name on it called strong nuclear force that like holds all together the protons and neutrons within that densely packed nucleus. Still science is still doing further studies into understanding what is binding all of that together. But whether or not we're able to describe it with particular scientific terminology or not, we do know that the Bible expresses to us that all things hold together in Christ. Christ is the one through whom all the worlds were made. He's also the one through whom all things hold together, as Colossians 1:17 says. So we know that God is not only the creator, but he's the sustainer. He's the one holding all things together. All right, and I already talked about the band stability and nucleons. All right, so element X has a half-life of 2 minutes. How long will it take to decay to 1/8 of its original radioactive material? So if it has a half-life of 2 minutes, and we're wondering how long does it take to get to 1/8, we have to ask the question, for there to be 1/8 left, how many times do we have to have a half-life to get to 1/8 of something? Well, we know that 1/2 times 1/2 would be 1/4. So if we multiply that by another half, 2 times 2 times 2 would be 1/8, which means we had how many half-lives to get to 1/8? 3 half-lives. So 3 half-lives. So if the half-life is 2 minutes, and we want to know how long are 3 half-lives, we just have to take 3 times the 2 minutes, and we should be able to get to our answer, which would be 6 minutes, right? All right. If element Y has 70 protons and 100 neutrons, it is probably, so remember what I was telling you before, whenever something has, as we get higher and higher with the number, it goes from needing 1-to-1 ratio for protons to neutrons, to then almost 1.5 protons to neutrons. And so in this case, this is very close to that 1 to 1.5 range, and so we might be hazard to guess that it's somewhere around the level of stability. But again, we can look at this on the actual band of stability. And again, this is really, really small to look at here. But we're looking for the actual dots to see where this lands. So you can do that with each of these. For cobalt-60, is it stable or not? So that would mean that it has 27 protons and 33 neutrons, right? Because we know that this number 60 is the protons plus neutrons. So to get the number of neutrons, we just subtract the number of protons from 60, which would give us 33. So we would look here and find the number 27, and then find the number 33, and zoom in, and notice here, this is really, really small, But notice that this is 1 away from a point of stability, so it's actually yellow right there, so it's not stable at that exact number. So it's an unstable radioactive nuclide. What type of radioactive decay, if any, are the following nuclides most likely to undergo? So this is a question of whether or not it has too many or too few neutrons, and which way does it have to go. So for argon-38, the nuclide has 18 protons and 20 neutrons. Remember, we get to this number of neutrons by taking this number, the 38, and subtracting from it the number of protons. That gives us 20 neutrons. So we have 18 protons and 20 neutrons. So we look at the number 18 and the number 20, and note right there, it's actually a colored in dot. So that's actually a point of stability. Intersection is in the band of stability, therefore no radioactive decay occurs. What about thorium-230? So again, it's going to be number 90. The Z here is larger than 82. Any element beyond 82, remember, is naturally radioactive. It will be decaying towards lead. So alpha decays most likely because its atomic number is greater than 82. What about aluminum-34? So again, we're going to look up 13, and then 13 plus what equals 35? Well, it's 22. And now if we zoom in there, notice that we have a yellow dot there. It's not stable. But beta decay is most likely here because the nuclide has less than 82 protons, and when plotted on the graph, it falls above the band of stability. All right, so nuclear stability is this band of stability where nuclides that do not undergo radioactive decay. So magic number is the number of nucleons in a full shell providing for its stability. So how many protons plus neutrons need to be there in order for the nucleus to be stable? All right, which brings us to the final section of chapter 20, which is using nuclear chemistry, and talk a little bit more about some applications of nuclear chemistry. In a nuclear reaction, atoms can send out particles and rays, changing their identity in the process and releasing huge amounts of energy. Alchemists, remember when we talked about chemistry very early on in the year, we talked about alchemy and their attempt to try to transmutate lead into gold and their failure to be able to do that. But we talked about how alchemy did provide a lot of apparatus and helpful work that led towards modern chemistry, but they were not successful in changing lead into gold, one element into another. It's not possible to chemically change an element into another element because chemical reactions happen, remember, deal only with the electrons. The only way you're going to change the element of something is if you deal with the protons, which happens in the nucleus. And so you need a nuclear reaction in order to bring this to pass, not a chemical one. So transmutation does occur with nuclear bombardment reactions because the number of protons changes. So there's two types of this. There's both fission, which involves splitting the nucleus, which then makes new elements and releases millions to billions of times the energy of chemical reactions. It's powered by this famous equation coined by Einstein, E equals mc squared, where E equals the energy, m is the mass, and c is the speed of light. Notice here a very, very large number. And that very, very large number, notice, is being squared. So the amount of energy that is produced is the amount of mass times the speed of light squared. A lot of energy. So here, uranium-235 being bombarded by a neutron is made into here, notice through this neutron, breaks apart the uranium atom into barium and krypton plus 3 neutrons and a whole lot of heat. Here, uranium-235 bombarded by a neutron, yielding two different elements, cesium and rubidium, plus two neutrons and a lot of heat. So in these cases, a neutron is bombarding uranium, it's splitting, and when it splits into a couple of different elements, and some additional neutrons are released, and a lot of heat. Now, notice that you had additional neutrons that were released. This allows for a chain reaction. One neutron hits a nucleus, splits it, releasing more than one neutron. And then those neutrons hit other nuclei, which causes other nuclei to split and release more neutrons. And on this process goes, thus called the chain reaction. So in a chain reaction, a fission reaction, this neutron comes in, hits the nucleus of one, splitting it apart. Here we have two neutrons that came off, which hit into another nucleus, which splits them apart, which then each in turn create two more neutrons, which then hit four other ones, which split them apart and create now 8 neutrons moving out. So you see how this chain reaction happens, and it happens very, very quickly. And with each one of these splittings, you get lots and lots of energy. So you kind of see this play out. So critical mass is the smallest amount of radioactive material that is necessary to sustain a chain reaction. You have to have a certain amount of stuff in order to get the ball rolling. But once the ball's rolling, it really starts taking off. But you have to start with a critical mass, a certain amount of material, in order to sustain the chain reaction moving forward. So in a nuclear reactor, uranium-235 heats up water to make steam, which then powers a turbine to make electricity. And the way they keep this under control is they have these control rods that absorb neutrons that slow the reaction. So in the case of like the atomic bomb, it's on purpose let to just run out of control and just cause a huge amount of destruction. But whenever we're utilizing this technology to produce energy, we have to control those neutrons that are splitting out to make sure that they don't hit too many other atoms to split too many things all at once. You have to keep them under control. So these control rods absorb those additional neutrons, which slows down the reaction. Heavy water with deuterium uses hydrogen with a neutron to absorb more energy. So here's the deuterium atom. So it looks like hydrogen, but it just has an additional neutron in it, and it's able to absorb more energy. But you still do have issues with nuclear waste and radiation, even from nuclear power that's produced relatively cleanly when compared to coal or something like that, but you still do have nuclear waste and radiation. So chain reactions begin when radioactive materials exist in amounts above the critical mass. So the atomic bomb is an uncontrolled chain reaction, like a fission reactor, but it has no control rods. It uses explosives to ram together two sections of uranium, which are shaped like halves of a baseball. When these come together, and then the reaction just starts taking off, and there's nothing to control the speed at which those reactions are taking place, lots and lots of energy are created, produced. Now, fusion occurs when hydrogen atoms fuse to form helium, and this also releases energy. This is what powers the sun, hydrogen being built into helium. Problem, though, is it requires a temperature of 100 million Kelvin to break even on energy. So you have to have that amount of temperature in order for the energy going in to produce energy going out that's of equal magnitude. Anything below that, you're having to put more energy in than the energy that you get out at the end of the fusion reaction. So possible solutions to this dilemma have been using magnetic fields as a containment field in order to hold this while this is taking place and create types of temperatures that need to be there in order to foster this fusion reaction. So a possible energy source of the future would be found here in fusion, where we could produce, H2 from water. H2 being formed into helium, releasing energy, would be very little radiation problems, would be no waste. Seems like a really, really great energy option for the future. Now, the hydrogen bomb, in case you didn't know, is a fusion bomb. The reason why it's called a hydrogen bomb rather than the atomic bomb is because in a hydrogen bomb, it's fusing hydrogen into helium. You actually are fostering a fusion reaction, which creates tons and tons of energy, or produces tons and tons of energy. But in order to do this, they use a fission bomb first to achieve the high temperatures that are required, and then set forth the fusion reaction, which then produces even more heat and energy. But obviously, that sort of system wouldn't work very well in a fusion reactor. Like, how would you keep all of that under control? So this involves putting two small nuclei. Which process involves putting two small nuclei together? When we're putting things together, it's called fusion. When we're breaking them apart, it's called fission, right? But this is called fusion. Which process produces virtually no radioactive waste? Again, that would be fusion. Fission does create radioactive waste. True or false? Elements beyond uranium would not exist if we didn't make them in the laboratory. This is true. So in nature, the only thing you find elements-wise is up through uranium. Anything beyond uranium is produced in the laboratory or as a result of nuclear bombardment. The problem with fission reactions is that they require enormous amounts of heat to initiate them. This is false, right? It's fusion reactions that require enormous amounts of heat to be initiated, not fission. So elements beyond atomic number 92 are radioactive and do not occur naturally. These trans-uranium elements, 93 and up, did not exist on the Earth until the atomic age. Just a couple of last things to mention. Nuclear binding energy, strong nuclear force, is that which holds the protons and neutrons together. I think I did mention that a little bit earlier. Mass defect is the difference between the mass of the nucleus and the combined masses of its protons and neutrons. This is a really fascinating little part of nuclear chemistry, and that's the idea that if the nucleus is made up of protons and neutrons, if we add up the protons and the neutrons, we should get them the mass of the nucleus. But there's a slight difference in mass between the total mass of the nucleus and the mass of adding up the protons and neutrons. This is called mass defect. Nuclear binding energy is so great that when it is given off, the products weigh less. E equals mc squared. Well, Genesis 128, I'm going to kind of end our class lectures together with where we started off. Remember, we began this by talking about the creation or dominion mandate that God gave to us as humanity. We've been meant to exercise a wise dominion and to subdue the earth. But by this, it means that we're supposed to exercise a wise rule, not lead towards the ruin of the earth, but trying to maintain it and take care of it and make use of it for our benefit, which means being reasonable, but also being careful. And these decisions are difficult ones, whether or not various ways should be environmentally safe. How are we trying to help our fellow man? These questions are difficult ones and ones that maybe many of you will maybe be involved in. We live here in Houston, an energy corridor, where there's decisions regarding how do we produce energy efficiently and safely, economically, in a way that people can afford it and benefits other people. Meanwhile, it doesn't harm the environment in irreparable ways. So these are all questions that you're going to have to be probably working through. Just as a couple of bad examples, right, of nuclear energy gone wrong: Chernobyl, 3 Mile Island. So there could be human error that causes nuclear meltdown of a reactor. Chernobyl, there could be poor design that's been put in place. But these are issues that have to be thought about when it comes to nuclear energy. The book even has at the very end of the chapter a discussion of fusion reactor that's trying to be put together. And I think it's on page 547. The ITER fusion reactor is designed to test the feasibility of generating electricity using fusion energy. A pretty interesting diagram that you can take a look at there. One other thing I wanted to mention in this chapter that I didn't mention already was that there is a facet, I think it's in section A, yes it is, on pages 532 and 533, talking about the radium girls. You should really read that as a point of interesting history where they were putting radium right as they shortly after it had been discovered, they were putting it on the hands of like watches, and the way they did this was with women. They would be in a factory and they'd be painting that radium onto the watch faces, and then some of them would even put it on their fingernails or on their teeth. And they would scare their friends, as they glowed in the dark at night, because at the time they didn't realize that this radiation was actually hazardous to your health. There were lawsuits that happened as a result of this. Most of those women actually died excruciating deaths because they hadn't done enough study on knowing what the products of these radioactive materials would do. There were plates made out of these things. There were radioactivity was even used as like a health thing. They would line like water coolers, and people would drink water. And they would call it radiated water, so you get more energy supposedly out of it. People not knowing that they're introducing harmful radiation to their bodies. So this is one of those cases where advances in science and understanding technology, there's some wonderful benefits that can come from it, but there's also potential hazards that have to be considered and thought through. Remember, science itself doesn't give us the materials that are needed to make moral and ethical decisions regarding all of this. And this is why we as Christians have to always recognize that whatever developments happen in science, all of our thinking about science, all of our implementation of what we've learned in science needs to always be submitted to the lordship of Jesus Christ. And we're so thankful that the Lord has given us his word, given us the Bible, which provides us with clear guidance as to how we're to conduct ourselves in this life. Well, I hope you guys have a good time reading through chapter 20 and learning more about nuclear chemistry. You do have some assignments to do in these sections, and please do reach out if you have any other additional questions. Otherwise, I'll be sending you guys in the coming weeks information on how to do further review for the final for the semester. But please reach out to me if you have any additional questions. Thanks so much, guys. Love ya. See you later.